Okay, we're good. Thanks, Ken. Hi, everyone. Thank you all for coming. My name is Luis, and I am the section chair for the AIAA LA section. Today, we have a pretty special talk lined up for y'all. Very excited about this topic, and I'm very excited about our speaker, Miss Angelina Suboy. I'm gonna tell you a little bit about her. She's a programmer and security researcher with an interest in the intersection of satellite technology, artificial intelligence, and signals intelligence. She is currently an undergraduate student majoring in electrical engineering at Caltech and the founder of Stellarix Labs, a research and development initiative focused on building autonomous space systems, electromagnetic defense tools, and AI-driven platforms for geospatial and orbital intelligence. Today, she's prepared to talk Seeing Earth Through AI, LLM Augmented Geospatial Research with Satellite Imagery. So, with that being said, I'll turn it over to Angelina.
Thank you so much for the introduction. Today I'm going to be giving a foundational overview of how artificial intelligence tools, there's been a recent surge of large language models within the past years, and I really wanted to explore the intersection of airspace tooling and publicly accessible airspace tooling, specifically for Earth observation satellites, and how that can be integrated with large language models such as the GPT models, Llama models, and so forth. Today is going to be a pretty introductory presentation that's going to be covering the foundational concepts underlying remote sensing, and then we're going to be covering how we can apply those concepts to understand Google Earth Engine and how we can apply remote sensing techniques to Google Earth Engine's satellite embeddings dataset in order to conduct large language model facilitated research. A little bit about my background. I've been working in the aerospace industry for the past 2 years, and I've been in the software industry for about the past 8 years. I worked previously for Impulse Space and an assortment of aerospace companies as a contractor. I'm currently an undergraduate at Caltech, and I'm passionate about the intersection of artificial intelligence, satellites, and signals intelligence. An overview of what we're going to be covering in this talk is, firstly, we're going to be covering the principles of Earth observation, so how satellites with onboard sensors, both passive and active sensors, are able to analyze images of the Earth in order to conduct research such as agricultural monitoring, urban restoration, and so forth. We'll then cover Google Earth Engine and embeddings provided by Google Earth Engine and how they can be applied in order to conduct remote sensing research. And then finally, we're going to be covering the AI section of this talk, where we're going to be covering large language models and how they can be used to augment and further analyze the publicly accessible data provided by satellites in order to answer fundamental research questions. So put simply, Earth observation is about acquiring data about the Earth away from the surface. So this is contrary to ground-based sensors. So ground-based sensors such as seismometers, which detect for earthquakes, or temperature sensors, which are ground-based, have a limited view of the Earth because they're not in space. So they don't give us a holistic picture of things that are going on at a global level. However, with the advent of specialized sensors on board of satellites, we're able to get a really good holistic picture of the Earth in order to conduct more global climate research, agricultural research, and so forth. So the first Earth observation satellite that was specifically for remote sensing was the Landsat-1, which was deployed by NASA in 1972. And this provided an entire catalog of public images that analyzed Earth's land cover, such as water coverage, terrestrial bodies, and such. And now we're at the point of where we have multispectral, or even hyperspectral, advanced specialized sensors on board of satellites. An example is the Sentinel-2C, which is part of the Sentinel family of satellites, which was founded by the European Space Organization. European Space Association, pardon. And that satellite is specifically for collecting optical data about the surface of the Earth in order to analyze vegetation, water, land cover, and more. So the reason why I decided to pick this topic today is the recent surge of satellites and market demand specifically for remote sensing data and analysis using AI. So with the accessibility of lots of commercial launch providers, the Falcon 9 being a very dominant launch provider, alongside other alternative options such as the Neutron rocket from Rocket Lab, there has been a surge of satellites that have been deployed into various orbital configurations, and that also encompasses Earth observation satellites. So you can see back in the 1950s, there was hardly any satellites being deployed into orbit, but now in the 2020s and so on, you can see an exponential rise of satellites being deployed into space. And we're also seeing another trend come up where we're seeing a shift from governmental flagship projects, which are like large satellite projects which cost millions of dollars, such as the Landsat and the Sentinel series, to more smaller commercial constellations that are being driven by startups. And this is mostly due to the launch, the cost to launch a satellite. The cost to launch a satellite has significantly decreased because of the accessibility of launch providers. And now startups can launch their satellites perhaps under like the tens of thousands of dollars to have their own satellites put up into space. And we're also seeing a lot of software as a service startups piggyback off of this trend where they're analyzing pictures taken from these satellites in order to provide more analysis for research and other commercial endeavors. So the applications of Earth observation and remote sensing are manifold, and it has fundamentally revolutionized a whole range of industries, mostly because it provides a lot of advantages over traditional Earth observation systems. And some of those reasons are because one, when you have when you have a satellite in orbit, you have complete coverage over the globe. The field of view of a satellite in space is much greater than another field of view of a man-made object such as a UAV. So they have an advantage in that regard. They also provide continuous coverage due to their orbital configuration. They're going to be consistently covering specific areas. And there's specific satellites called geostationary satellites, which serve the sole purpose where their orbital velocity matches the Earth's rotational velocity. So if you look up at the sky at a geostationary satellite, it will stay at the same place above the ground. And those are very handy when it comes to Earth imaging and Earth remote sensing because they're effectively covering a specific plot of land over the Earth. And lastly, Earth observation satellites provide sensors on board that allow for a wide range of data coverage, which typical cameras were limited by. Specialized sensors span a wide range of the electromagnetic spectrum, allowing us to collect more data about the Earth. So some applications of this include wildfire response. It can also include disaster response for hurricane analysis and land coverage analysis for specific groups such as farmers. I want to go over some case studies of how Earth observation satellites have been applied in multiple industrial sectors. So one primary application of Earth observation is within the agriculture industry. And there was a case study of this where a lot of sub-Saharan African farmers were using satellite data in order to do cropland mapping over sub-Saharan Africa. And this is because regions of sub-Saharan Africa are primarily dominated by smallholder farms growing crops. And there's a lot of commercial implications where if you're able to distinguish these smallholder farms from the other existing landscapes, such as the savannas, you're able to help these farmers track for seasonal changes with their crop growth and also track their crop yields. So they were able to leverage the Sentinel-2 dataset in order to classify these small farms across the region and provide that data to those farmers. Another interesting application of Earth observation satellites is for disaster response. And this is a very recent example with the restoration and analysis of the Los Angeles Eden Palisades fires that occurred earlier in this year. I'm sure many of you guys had families or were directly impacted by the fire yourselves. And there was a small, medium-sized company called ISI, which owns a fleet of synthetic aperture radar satellites. And synthetic aperture radar works really good because it uses a microwave frequency of the electromagnetic spectrum that penetrates through ground and is able to detect for wildfire pretty readily. So this company was able to provide a consolidated damage assessment report and was able to classify destroyed buildings within thousands of acres of land. And lastly, I think this is one of the most interesting applications of Earth observation data is defense. And one case study of this was maritime awareness of dark vessels. And what dark vessels are ships that don't have an AIS system on board. And what vessels with, typically vessels have an AIS system, and this is used to identify the vessel, including its heading, its speed, its location, and so forth, using radio technology. However, there are a fleet of dark vessels that are typically employed to conduct nefarious activities, such as oil spilling, smuggling, and illegal fishing that do not have an onboard AIS system because they want to stay under the cover. And in order to spot these dark vessels, ISI was able to spot them using their synthetic aperture radar satellites. Earth observation fundamentally operates with the underpinning principles of the electromagnetic spectrum. I'm sure most of you guys have learned about this in your high school physics class. And what the electromagnetic spectrum encompasses is a wide range of electromagnetic phenomena, such as gamma rays, X-rays, all the way down to radio waves that allow us to characterize different things, such as color, heat, and so forth. And satellites have specialized sensors that are able to allow us to access pretty much a wide span of the electromagnetic spectrum, while typical sensors, biological sensors like our eyes, are confined to the visible range. Satellite sensors can see a lot more, and we're able to derive a lot more information about the Earth. So utilizing the principles of the electromagnetic spectrum, we can derive things such as spectral signatures. So materials on the Earth have their own unique spectral signature. And this depends on the material characteristics of the land cover of the Earth. So things such as soil absorb a lot more within the mid-infrared, and they have typically they have a higher reflectance value than things such as water or green vegetation in specific segments of the electromagnetic spectrum. And by leveraging these spectral signatures to classify different objects, we're able to analyze things such as crop monitoring, changes in weather, and other disaster response cases. So there's two types of satellite sensors that are typically used. There's passive sensors and active sensors. Passive sensors detect electromagnetic radiation reflected off the Earth from natural sources. So a wide range of passive sensors are optical sensors that detect for visible light that are reflected off the surface of the Earth from the sun. But there's also infrared sensors that detect the actual heat of the Earth because the Earth has a heat from it because the molten core. So typical things have a spectral signature within the infrared band, which is used for analysis. There's also active sensors. Synthetic aperture radar is old, but it leverages the microwave frequency. And what it does is it's an active sensor, so it means that the satellite itself is emitting its own electromagnetic pulse and getting its own pulse back in order to derive things such as altitude and material composition. Two other forms of active sensors include LiDAR, which uses light, and radar altimetry, which uses traditional radar techniques. Spectral bands are grouped portions of the electromagnetic spectrum used to detect specific materials and phenomena. And bands are like filters, so you can kind of think of like red, green, and blue independent colors of the visible spectrum as their own band. So in the picture on the right, you can see that there's 3 bands, one blue, one green, and one red. And what satellites do, or satellite data processing sensors do, is that they take each band and they combine them together in order to effectively make a band combination to create a visible image. So here are some more examples of band composites, which are combinations of bands. So you can see a typical true color image, which combines red, green, and blue. There's also false color image, false color urban, which are just different variations of different band configurations that the satellite utilizes. This is just a simple example of how a satellite camera would see things. So take a picture of 3 butterflies. One is green, the middle one's yellow, and the right one is red. So in the red band, you can see that because there's a red filter applied, if you take a look at the normalized grayscale vector, the butterfly on the right that was predominantly red reflects really highly, meaning it's really white. The one in the middle, which was orange, still reflects pretty highly, meaning it's more white in value because it's close to red in the electromagnetic spectrum, while the green butterfly is completely dark because it's far away from red in the electromagnetic spectrum. So this is for the green band. So now you see the inverted effect where the green butterfly shows up as really white, while the red butterfly shows up as really dark. And then blue band, blue is slightly more towards the middle of the electromagnetic spectrum. So you can see that pretty much all the butterflies look dark, while the one that is green, which is closer to blue, appears a little bit more light. So using these band combinations, we get the color in the original image. So within a practical application, satellites have a wide range of bands. It's not just limited to 3, which is what we see. They have infrared, they have access to pretty much a wide range of the electromagnetic spectrum, so they can leverage other band combinations such as infrared in order to derive more material composition facts about the Earth. So to the left is a visible true color image of red, green, and blue. And then to the right is a near infrared false color band combination. And this is typically used for agricultural analysis, where you can see the healthiness of live crops. So healthy would indicate red in this case. Water is the dark blue color up to the top left of the image. And you can see dead foliage and soil is indicated in light green. And you can think that this has a lot of applications, especially within the farming industry and response to wildfires. Remote analysts also like to get creative with these bands. You can also perform mathematical combinations of spectral bands in order to get unique applications for research. So this is really helpful for wildfire research. So there's 2 indices that were developed called the Normalized Different Vegetation Index, and that's for monitoring vegetation health, and that's described by the mathematical equation. It just takes the near-infrared band and the red band, and it normalizes it so it's confined within a value between 0 and 1. You have the burn coverage, which is indicated by the NVR, which takes the near infrared band and the shortwave infrared band, normalizes it, and these two mathematical indices can give you a really nice plot of wildfire damage that occurs. So to the right is a visualization of NVR and NDVI pre and post fire. So the two main satellites of concern where we're going to be talking about Google Earth Engine are Sentinel-2 and Landsat-8. The band overview for these two satellites are shown there. You can see that both of them have pretty good band coverage, but there's also nuances in what they're able to occupy in terms of the electromagnetic spectrum. So it's good to know what satellite to pick when you're picking a satellite, which band coverage it has. This is more specifications on the Landsat 8 and the Sentinel-2. You can also see bands as well. Landsat 8 has more bands. Sentinel-2, Sentinel-2 has more bands. And you can see the wavelength occupancies and the bandwidth are slightly different amongst the satellites. So moving on to Google Earth Engine. Google Earth Engine is a very simple cloud-based platform for geospatial analysis. It makes geospatial analysis very beginner-friendly and easy, and it allows you to interface with it using JavaScript to create custom scripts using their code editor. You can also access it using their Python API. They have access to petabytes of satellite imagery, and they have a diverse set of satellites involved within their fleet of data, including the Landsat series, the Sentinel, and specialized sensors such as MODIS. Google Earth Engine has a data catalog as well, which encompasses a collection of accessible data for specialized research. Some highlights within the data catalog I was able to find were specific coverage of the Canadian Digital Elevation Model, which provides elevation data over Canada. There's also RGB composite models. So this one is specific to a town or a city in Germany called Brandenburg.
Question.
Yes.
So let's talk about those data catalogs.
Yeah.
What are we seeing in terms of refresh rates or population of the most latest and current data?
Yes, that's a really good question. So most of the data provided by the Google Earth Engine, satellite embeddings data specifically, is near real time. So the latency of getting the data is within like 10 to 15 minutes. You might have to correct me on that, but it's within that range. But that's a really good question because some satellites, because of their orbital period and the orbital configurations, they are slower to obtain the data. So satellites within low Earth orbit are a lot faster to get refresh rates and data because they move faster around the Earth. But satellites up in GEO can take a lot longer because it takes longer for them to complete an entire period of their orbit. But it also depends on the fleet itself because if a fleet has more satellites in it, then you can update more data. But typically low Earth orbit satellites are faster because of the latency of the signal that between Earth to the satellite, while GEO satellites, they're about like 35,768 kilometers of the surface of the Earth, so it takes longer.
And it's commercial off the shelf, right? So anybody can go in there and plug and play the data?
Yes, yeah. Unless it's like a defense satellite or like a private satellite, yeah. Yeah, but all the data is available on the catalog. So within Google Earth Engine, they provide a specialized data set called the Satellite Embedding Dataset, and this has a lot of implications for artificial intelligence. And a brief overview of this data set is that it's a 64-dimensional geospatial embedding. We'll talk about what that means in a moment. But it allows researchers, it removes a lot of overhaul in the research process because it doesn't require a lot of extensive data pre-processing. which involves like cloud masking. So if you have an image, but there's a lot of cloud coverage over it, a lot of researchers in the past, they had to provide specialized algorithms in order to get rid of those clouds. But with these embeddings, all of that is taken care of for you. So things such as cloud masking, speckle filtering, and other things that can obscure an image and limit the accuracy of your data are completely eliminated. And another great thing about this embedding data set is it works out of the box. So you don't have to leverage a lot of traditional deep learning techniques such as fine tuning that uses a lot of extensive computational power.
Some attending online, they're saying maybe without a microphone, the voice will be better. So it's okay, we kind of turn it off or to try it out. Yeah, and then you, because they can hear you from the TV there. They feel that might be better.
Okay, is this better? I can't see what they're saying.
Okay. Dennis, is it better? Catherine, without the microphone, is it better? You seem to say yes.
Okay.
But it's okay for you? You to speak.
Yeah, it's okay. I can project out loud.
Okay, all right. Sorry for that.
So a little bit more context of what a satellite embedding is. Put simply, an embedding is a numerical representation of a complex data set. So when you're training a machine learning model, computers don't understand abstract concepts that humans do, such as words. So we need to find a way to process things such as words, color, abstract things that we can perceive into numerical data. So a simple example of this is word-to-vec. Word-to-vec is a typical technique that's used primarily for natural language processing, where you're distinguishing words from each other. So you can see on the chart to the left, vectors, so they're initially represented as vectors, which are arrows pointing out from the origin point. And you can see words such as girl and boy are very close together. Queen and king are close together. Sport and game are close together, but those groupings are far apart. And this is used for a lot of like contextual understanding and understanding lines of text. And each word for this to work is represented as a vector embedding, and a vector is an array of numbers which numerically represent what the word means. So satellite embeddings in the context of satellites are slightly different because they encompass different things. They're not words. So embedding characteristics that are included within a satellite embedding include spectral data, which we discussed before, which is the reflection of electromagnetic energy off of the surface of the Earth. There's also spatial data involved, so data that encompasses seasonal changes, day-to-day variations, hourly variations is also encompassed. There's also spatial data, which takes into account the context of the environment around where the data was collected and relationships and the interplay of those relationships with the data. And then finally, we have derived features. So this is higher level data. There's different levels when we're considering satellite imagery and processing. Level 0 is like the raw binary. Level 1 is like the binary with like metadata. Level 2 contains slightly more information. But as you progress up different levels of satellite imagery, it gets more and more redundant in the sense that more data is packed onto it, and it's further from the truth, which is given by the binary collected by the sensor on the satellite. But it also includes derived features such as vegetation, water, soil, and so forth. So these embeddings can also be represented as vectors, such as word-to-vec, which I mentioned earlier, but these are confined within a 64-dimensional sphere representing the globe of the Earth, and each orientation of the vector has its own unique embedding to it, which contains an enormous amount of bands totaling up to 64. So if you want to plug and play and train your own models and access this Google Earth Engine satellite embedding dataset, it's very easy. All you have to do is log into Google Earth Engine using your Google Earth account. You do have to register your project, but it's fairly easy to do if you're affiliated with a academic institution or if you're conducting your own personal research. When I applied to register a sample project I was working on, I instantly got access, so this is something you can try out yourself. And when you get access to the script engine, all you have to do is load the satellite embeddings collection in JavaScript. So this is an example of how I was able to use Google Earth Engine to conduct research over the surface of Kenya. So the location I chose for my research was southern Kenya, and there's different ways you can define a region in Google Earth Engine. One, the most rudimentary way of doing this is by establishing a bounding box. So here I don't know if everyone here is familiar with programming, but it's pretty straightforward. I defined ROI as a variable. ROI standing for region of interest. You hear that a lot within Earth observation. And I established it to be a rectangle, which encompasses squares. And I just provided the latitude and longitude coordinates of each point in that square in order to find the region I wanted to analyze over Kenya. One tip when you're doing this is finding custom polygons online. So if you don't want something as simple as a square, you want something more elaborate, like a specific region. So this is for a project I did which analyzed the Palisades and the Eden fires over Los Angeles earlier this year. And I was able to download that custom shapefile from LA County's ArcGIS website, and there's a lot of public organizations out there that provides shapefiles which you can implement into your Earth observation pipeline.
Question.
Yes.
So how are you counting for error and variances? Is that a big challenge right now?
In terms of like the data analysis or like the data on the
When it
satellite,
comes back?
where it comes back and like things such as like the atmosphere could like
Could be many things, right?
Yeah.
There could be just some variance in maybe temperature or water or salinity, right?
Yeah.
In the ocean. Is that a big challenge right now that we're experiencing? And if so, how do we account for that or get after that?
I would say there's two sides of the coin when it comes to addressing that issue. So the researchers have it easy, mostly because like Google carries most of the grunt work for you.
Okay.
Because they provide it as an embedding, and because it's an embedding, it has all the pre-required like pre-processing steps that it goes through beforehand, such as like cloud masking and stuff. So Google takes care of it for you. But if we think of it from the organization or like the company's point of view, then yes, obtaining like real-time imagery is a big challenge in and of itself. You need a lot of satellites. And also there's a lot of things to account for when you're extracting signal from a satellite. So a huge problem is attenuation. Satellites are 2,000 kilometers or up to geo, and that's a long distance for a signal to propagate back down to the atmosphere. And you'll face a wide range of things that could make your signal defunct. This could include cosmic radiation from the Bad Nile belts. This could include
Solar storms.
Yeah, coronal mass ejections, the intrinsic attenuation from the atmosphere that can degrade your signal over time, which is intrinsic to the Earth. And there's also things here on Earth, like cell towers. Everything is always constant. Lots of electromagnetic devices are constantly beaming out
Pollution.
energy,
Right.
and it effectively creates pollution that degrades the signal. So there's a lot of like signals intelligence work that has to go on, that has to be analyzed like under the scenes, but it's not like Google has so much economic power that they can like afford a huge satellite dish to receive communications from the satellites, and they have so much personnel on board to handle like the algorithms, and like they have a wide range of like restoration methods to improve the fidelity of the signal.
So it's pretty reliable, pretty
Yeah,
solid.
I would say it's pretty.
I'm not gonna mention rates, but maybe like the confidence level, right?
Yeah,
It's pretty solid.
I'm not sure about like, the exact number, but I would be suspicious if it was like under like 95.
Oh, wow, that's pretty good then.
Yeah. So another characteristic to take into account when you're conducting Earth observation research is specifying the time and the range you want to collect your data over. So in this case, I wanted to analyze that spot over Kenya for 1 year, the time span of a year, starting from 2019, from the start of the year, up until 2020 at the same date. So that's what that means in JavaScript. And if you're not don't have a lot of familiarity with programming, there's also an easier language variant to this called Python, which makes it a little bit more simpler in terms of specifying the syntax of the language. There's also a wide range of documentation and tutorials provided by Google, which I'll be listing at the end of the presentation, that makes the process of creating your own scripts with Google Earth Engine fairly easy. And with 3 lines of code, I was able to visualize the bands of the satellite embedding data over that region of Kenya. And for the 3 bands, if you look to the far right of the first line of code, those were specified as A3, A16, A8. Those were random bands I wanted to visualize, provided from the Google Earth embedding data set. Like I mentioned before, they have a total of 64 bands, each containing their own unique types of data. So I wanted to mention that you can definitely play around with the band configurations and the band types you decide to choose. And I was able to visualize this by using the add layer function to visualize the embeddings on top of the surface of the Earth. If you want to access this introductory script, I put it up onto a GitHub repository. It should be 18 lines of code. You can play around with it yourself. You can copy and paste it into Google Earth Engine, and if you press the run button on the top, it will not only show you the map on the bottom, but will also apply the layer on top of it and show you the visualized bands alongside the script. That was a very introductory script that showed the capabilities of Google Earth Engine. Google Earth Engine has a wide range of applications, they include unsupervised learning, where you can cluster pixels into groups without any labeling beforehand to reveal natural patterns about the Earth. So you could reveal contrast between bare soil and vegetation across a specific land surface. There's also a supervised approach, where you can train classifiers using labeled samples, pre-labeled samples, to categorize land cover, crops, and urban areas. You can do this using labeled data beforehand that you import, or you can label it yourself by going onto the map and putting markers on the map and specifying which regions you are interested in and labeling them to classify a specific model. There's also regression involved, where you can predict continuous variables over time. So you can see how vegetation index changes over time. You can see how pollution changes over time, surface temperature, and so forth. And then there's also similarity search, which I think is interesting. So by picking a specific point or a region you're interested in, you can see regions that are very similar in that regard at a different location. So let's say you want to get farmland, farmlands that, if you wanted to like get a result of farmlands in Germany that is similar to Kenya in terms of their cropland yield, Google Earth Engine is able to provide that for you. Once you log into Google Earth Engine, they also have a set of demos that they list as scripts within the demo section, and they provide a wide range of classification models, models where they do regression and plot everything on a map. So it's able to extract numerical information about a phenomenon that's happening on Earth, and it's able to put that on a trend line for you. So let's say like you wanted to get like the variation of vegetation over Los Angeles seasonally, you can just put a bounding box around Los Angeles and see how vegetation changes as the seasons progress. And there's also really nice like classification models where you can classify terrain over Earth. So those are really good resources if you want to learn more about how to use the software. So I was playing around with deep learning imagery for satellites, and initially like this talk was going to be solely about remote sensing in satellites, but I found some interesting results when I was playing around with large language models in order to enhance the satellite Earth observation workflow. So large language models, you've probably heard of them before, they're everywhere right now, such as ChatGPT, Claude, Llama, so forth. They're pretty much an AI assistant that allows you to prompt it and it'll give you a response. And this is really pertinent when it comes to Earth observation in three main ways, I would say. So one is to obtain summaries of raw indices. So like if you want a tabulated report of the vegetation health, you can do that. You can also get reports on damage control, such as drought severity and infrastructure damage over a specific region. You can also create labels for supervised machine learning. So this could be used as like a prerequisite step before you train your own model. So let's say if you had like a supervised machine learning algorithm that needed like labeling of data, because that's like the first step of a machine learning model of that type. This could do that for you, and that saves a lot of like manual grunt work where instead of like labeling or like drawing boxes around specific regions of like vegetation yourself, Google or the large language model can do it for you. You can also prompt it to discover long and short-term trends that occur within Earth observation data, kind of like as a summary step after data processing is complete. One application of this I really enjoy playing around with and I recommend using is Chat2Geo. This is, I would say like an advanced GPT wrapper, but it has really cool visualization capabilities, and it contains a wide range of highly specialized satellite data to give you interesting insights. You can learn more about it on their GitHub repository. And on the back end, they use Google Earth Engine, and they also allow you to import custom vector data as well. So let's say you have geospatial data from a satellite that Google Earth Engine doesn't provide within your satellite embedding dataset. You can import that yourself. And it also includes a wide range of analysis toolkits for specialized Earth observation and remote sensing techniques, such as air pollution monitoring, urban heat visualization, and land cover. So one project, a brief project I did was analyzing the highway pollution levels in Los Angeles. So there's a chemical called nitrous dioxide, which cars and trucks emit, and they create this effect of smogging. So nitrous dioxide, when sunlight is fed into it, they create effects such as smogging. It's also linked to a wide range of medical concerns such as asthma and lung and cardiovascular stress. And I wanted to see how open source satellite data can be leveraged in order to see how the pandemic impacted these levels of pollution in Los Angeles. So Chat2Geo made this fairly easy. All I had to do was draw a bounding box of the region I was interested in. So I picked a highway area. This is, I think, the 405. It's directly northeast of Long Beach. And I specified the bounding box area, and I gave it a variable called highway. And you'll see at the prompt at the top, I asked Chat2Geo in order to analyze satellite data defined by that region of interest from a specific time range. So I specified March 2020 to April 2021. And I prompted a specific question addressing what I wanted to research, which was to summarize the levels of air and surface pollution and describe the time frame where the pollution levels were the highest. And insights I was able to extract from that was the lowest levels of pollution within the highway system of Los Angeles was between March and April of 2020. And this was primarily due to the COVID lockdown, so people weren't traveling as much. And I was able to, the model was able to access that data by synthesizing mobility data and data from the Sentinel-5P. Sentinel-5P is a specialized satellite within the Sentinel fleet, specifically for monitoring pollution indices. And it was able to show nitrous dioxide collapse across the collapsation of it across Southern California due to the massive reduction of traffic. I also asked it for the highest levels of pollution, and it detected that it was in September 2020, and that was mostly because it was Labor Day and there was a weekend traffic surge. There was also other environmental factors as well, including heat waves and wildfire smoke. It's always good when you're testing out a large language model to vet it with actual real data sources, and you can see that in this case it was correct. As of March 19th through March 18th of 2019, you can see that the nitrous dioxide level or pollution level of Los Angeles was significantly higher than compared to 2020 because of the lockdown. I'm sure most of you guys have heard of prompt engineering before. Prompt engineering is a way of refining the input of a prompt to get the most useful response. So it's like a way of helping the model understand what you exactly want in order to get the most useful data for your research. And specifically for Earth observation research, I found that anchoring the data set by specifying the data set you were interested in, and that requires a little bit of research online, but by knowing which satellite you're interested in and what that satellite does and what that satellite measures, you can greatly refine what the model outputs. And you can do this by specifying the data set, and usually data set names are published online. So you have to do a little bit of research, or you can go more broad and specify the satellite you want to get the data from. Another helpful technique is to define the region of interest. This not only saves you a lot of time, but it's also a lot more accurate because localized data is typically more accurate than generalized global data. And it's typically it's fairly easy to define. All you have to use are geo-coordinates, a bounding box, or a custom polygon you can download as a shapefile from an online internet source. Specifying the variable, so this could include NDVI for vegetation, nitrogen dioxide for pollution, AOD or land cover mass, and then stating the objective. So finally stating what kind of process you wanted to run. Do you want it to classify something? Do you want it to classify rivers? Do you want it to classify cropland, regression, trend detection? Do you want it to analyze for patterns over time? So you're being very specific to the model and prompting it to give you what addresses your research question. And optionally, you can add a little bit more context in order to get out more nuances in the data you are seeking. So an example of the prompt, so this is a refined prompt of what I asked Chat2Geo earlier, and it's analyze the satellite data for the region defined by the region of interest from March 2020 to March 2021 using the Sentinel-5P dataset. Summarize the levels of air and surface pollution and describe the time frame where the pollution levels were highest. So you can see this prompt hits all the 5 criteria I listed before, which specifies the region, the date, the dataset, the objective, and adding the optional context. So I would say refining the prompt is the easy part of this process. I would say the harder part is going through the grunt work of formulating a good research question. And I would say a few tips for this would be to pick a topic of relevance or expertise, something you have prior knowledge of beforehand. This makes all the subsequent steps a lot more easier, and it saves you a lot of time in terms of the research you need to do in order to find specific variables you want to measure. Secondly is pinpointing which variables the satellite dataset measures. And I found that looking through Google's data catalog was really, really good for this, and knowing which variables you want to measure. So for example, if you wanted to measure pollution, then you need to understand what chemicals in the atmosphere can be detected by that satellite. If you want to understand vegetation growth, then you need to understand the band capabilities of that satellite so it can create a very accurate NDVI for you. Thirdly is where and when, what location do you want to specialize in, and what time frame are you interested in. And then lastly is a good research question should always finally lead to an impact statement, where how can the analysis of the data can be leveraged to have some kind of positive sociological impact. And that's really good if you want to get access to like research grants or conduct like impactful research that gets your foot in the door in terms of like organizational research or academic research. So an example of this would be coastal erosion, focusing on the shoreline of Palos Verdes. So first step was pick a topic of relevance or expertise. So in this case, it would be studying the coastal erosion and shoreline change under the rising sea levels. The second step is to find the variables the satellite dataset measures. So in this case, I picked the Landsat 8 and Landsat 9 because they provided visible and near-infrared composites, which were helpful in terms of conducting research. Where and when, where I wanted to specialize in the Los Angeles South Bay, and specifically Palos Verdes, because Palos Verdes has a very significant coastal erosion issue where you can see like the entire coastal cliff face. It looks like an avalanche, an avalanche of rocks can like form at any time. So I picked Palos Verdes because I felt like that was the area in Los Angeles where that issue was most pertinent. And when I wanted to study this from 2000 to 2024, and its link to impact was storm-driven erosion can threaten infrastructure, beaches, and coastal ecosystems, causing a wide range of not only environmental concerns, but also economic concerns as well. So putting those things together, I was able to get a research question which stated, how has the shoreline of Palos Verdes retreated between 2000 and 2024, and how does this observed retreat rate correlate with local sea level rise and storm surge frequency? If you're looking for research inspiration, I highly recommend looking through the Google Earth data catalog. They have a lot of really, really interesting and diverse data sets across a wide range of regions. They have like specialized data for specific states, specific countries, global data sets, and also for like different applications and composites. So looking through their data catalog is a lot of fun. Another tool I highly recommend is NASA Earth Data Search, and this pretty much gives access to years and years of satellite Earth observation data. specifically for MODIS and VIIRS, which are both active sensor systems on board of NASA satellites. And they consolidate all that data for you within a interactive website. And you can just look through their site. You can put a bounding box. It pretty much has like the same effective features as Google Earth Engine, but it's pretty much all of NASA data. And you're able to specify the time range, day and night, and get access to these data granules. In terms of models, I mentioned Chat2Geo earlier, which leverages GPT. I'm currently doing more research on this, and I haven't really found one model to be better than another in terms of research specifically for Earth observation. I know each independent model on this list, such as the GPT series, Claude, Gemini, Llama 3, Llama 4, and lightweight open source models such as Mistral, each have their own advantages depending on like your access to compute, like the safety of the data, the integrity of the output of the model. But for Earth observation, it's really up to you. I wanted to end this talk on how you can create your own local Chat2Geo. I created a version which you can download on GitHub. But it's good to know the engineering pipeline if you want to create your own custom Earth observation large language model yourself. So this includes giving an input to the large language model, having your own local large language model on your machine, local meaning that it's on your machine and not on the internet, passing it through the Google Earth Engine API, which yields you the Earth observation data, which then you can pass into a large language model to obtain a summary for it. This pipeline consisted of OLLAMA. OLLAMA is an open source program which allows you to run large language models locally. And I used OLLAMA in order to install Llama 2 locally on my machine, and then used the Google Earth Engine API. An API is like a link that allows you to get direct access to the data. And by consolidating like a few scripts you can together and downloading things onto your machine, you can have your own custom large language model that interprets satellite data for you and is able to give you actionable insights. If you're interested in learning more about the subject or tinkering around or playing around with any of these models yourself in relation to Google Earth observation, I highly recommend checking out Satellite Image Deep Learning. He interviews a wide range of researchers regarding Earth observation and satellites and how artificial intelligence relates to satellite data collection. So I highly recommend his blog and his interviews. There's also a $5,000 grant that Google is giving out to researchers who conduct their own research using Google Earth Engine, which I highly recommend. The Google Earth Engine tutorials are very, very helpful in terms of getting into the nuances of Google Earth Engine and how you can train classifiers. It walks you through unsupervised classification, supervised classification, and a wide range of other case scenarios. And lastly, all of the code for included in this presentation has been uploaded to the Stellaris Labs GitHub repository. Thank you so much. If you have any questions, feel free to raise your hand.
I guess we got And can you go back to the beginning of your presentation when you saw when we saw a lot of the providers?
Oh. Then
I think they can hear us.
I think I closed the presentation. I closed. Can you?
Oh, you close it. Oh,
Yeah, I did.
this is on the other screen. It's the bottom. PowerPoint. then you just click this. Right. First, you have to auto.
Thank you.
Well, this is a touch screen.
Okay.
Right, that was the chart where you had all the providers. Okay. Yep, so starting 2023, we saw like, I mean, that's massive, right, that exponential.
Yeah.
So, and by the way, apologies, not introducing myself. So Rick Garcia, US Space Force, we're at Elsevier. So working with NASA a lot. So what we were looking at doing is how we're gonna monetize, how we're gonna bring money and leverage and financial. I mean, we're working on building like a stock market, right? We were gonna build a New York Stock Exchange of space based on commercial companies, mining regolith on the moon, I mean, everything. We have conceptualized everything. And so one of the things that NASA clearly has told us, we're getting off Earth, like this is it, right? Like that's the look-see right now. In regards to current administration, it's like get off of environmental, right? The Earth science, it's being done. I think it's being proven here, right? I like your data because it's given a lot of context to that. And what NASA has told us, hey, we're going to go to Mars and beyond, right? They're very clear, and they want us as a Space Force to latch, like it's the Space Coast Guard, right? Those are some of like the theoretical talks. So my first question is, have you guys had a chance to work on observing the other planetary bodies, right? Europa, right? Europa moon, the icy moon, right? Salinity in the ocean under the moon of Europa. And then the other planets that are out there, right? That resemble Earth-like planets. So has any of your work or colleagues that you've come across, have we seen any growth in that technical side?
Yeah, in regards to like other planetary bodies. Like
Right, that resemble Earth-like planets, because I know we've discovered some, right? And can this capability
be applied to those planets?
Right.
Like it is applied to Earth.
Right.
Yeah, I've seen, so there's, for Mars specifically, I'm just most familiar with Mars. There's orbiters around Mars, and they've done altimetry. I think they had like a LiDAR system on board in order to like get the topographic structure of Mars. So I forgot like the huge volcano on Mars, Mount like Olympus. Like so if you've seen like those topographic like pictures on the internet where it shows like on a color map like the different heights and elevations of Mars, those were by Martian orbiters, and those were affiliated specifically with NASA. Other planetary bodies, I'm sure I'm not too familiar with, but NASA has the most permanent orbiters. And the great thing about NASA as an organization is they make most of their data accessible to the internet, so you can find that data. And I think it's a matter of like getting more people interested in those data sets and having more independent researchers get access to the data so they can conduct their own like analysis of it. But I would say, like analysis of orbiter imagery around Mars specifically is going to be very, very imperative, especially when we're thinking of colonizing Mars as a planet, because there's going to be a lot of things we need to account for, such as like the regolith structure, like where we can form a base. I'm sure like Robert Zubrin, who was a speaker here I think last week, he probably can talk about this all day.
I just interested, you mentioned it, I just came back from Johns Hopkins University, and we're just gonna dig holes. That's just the best, I think we're looking at some of those models on the moon, and it's just because it's gonna protect us, right, from radiation exposure and so forth.
Yeah, but for the moon, that's really interesting because I don't know too much about helium-3 or whatever, but I think helium might be like using orbiters around the moon can be a really interesting way to get insights about locations where helium-3 is concentrated. Mining companies can go there and you can build data to the mining companies.
Yeah, we found it in the the polar polar areas, the northern caps of the moon, where there's water, right? So the H2O signatures are closely related, you know, substance and material, but that. So our biggest challenge, coming back to the commercializing the space industry, right? We're just trying to, that's the big challenge. That's the big challenge, because we are gonna push out, and then we're gonna allow the commercial industry to take over, right? Whether it's, you know, a bald guy, you know,
Yeah.
that runs Amazon, or, you know, a guy that, you know, that's out there flying Starship rockets, or, yeah, Jeff Bezos, Elon Musk, and, but those are the biggest challenges. How do we commercialize the space envelope, right? Bigelow, whether we do inflatables in low Earth orbit, space hotels. That's the biggest challenge. And how do we bring, you know, if you want to talk about the stock market, liquidity to the market, and how do you make that a financial force? Those are the, and so what I'm seeing here is that's been a massive exponential growth.
Yeah.
That's completely unexpected. I know it was going to go big, but
I think it's gonna get
chart,
even crazier too. And then we're
Yeah.
gonna have to start thinking about like policy in regards to like traffic in low Earth orbit. That's already a problem with the Kessler effect. Like, you know, one satellite rendezvous with another satellite, and you know, with a ton of orbital debris that might have like you know, that might induce a lot of infrastructural damage in terms of.
we had the ADVS system talking to Pentagon and to Congress, you know, the one they use for the aircraft. And I think it was recently shot down, or I think it's just like kind of in a purgatory state, because there's a massive criticality to it, and but how are you gonna? I think there's still a lot of kind of finagling on how they're gonna wrestle that. But I'd like to get your take on what do you expect, and from your perspective. I mean, you've been in this field, right, for like a couple of, you know, 10 years. How do we get there? How do we finance? How do we make that a financial imperative, and how we're going to monetize this? Because I did, and I worked with a team, and we just, yeah, we're kind of at a stopgap right now.
Commercialize this for like large organizations like the US Space Force, or like.
And for everything
Just
on
like
Earth,
for
all
everyone.
all humankind. I mean, because we're gonna get off of the planet, right?
Yeah.
And that's the conversations that we're having. So how do you bring that market economy, you know, that $40 trillion space economy, right, to commercialize it? I'm seeing something here. It's just, I'd like to see what your take is. Is this just going to grow another exponential leap and bound over the next 10, 20 years?
I would say so. Yeah, I would say like aerospace, this is a bold statement, but like aerospace, I would say is like almost like second to third, like second to like to me, like software and like artificial intelligence at this point, to in terms of commercial growth. It's just I just seen, especially here in like El Segundo, there's just been a flourishment of like aerospace startups and small companies. Yeah, a lot of companies here were like initially employees at companies like SpaceX that decided to do their own thing. And here, there's an amazing ecosystem of venture capital investors and a lot of like networking programs that allow for the fruition of companies, and there's a lot of like interplay between these companies that allow for commercial growth and friendly competition to happen. So I don't think this like explosion of commercial endeavors within the space industry is going to dial down anytime soon. I would say it would be like a matter of like I don't know, like making sure people have the right like networking opportunities, and are able to like forge the connections to be able to start the companies, and also like preventing like dominant forces like SpaceX and like other huge companies like Blue Origin to like, you know,
be the only players in town.
Be the only players in town, like giving the small startups a shot.
So I want competition, right?
Yeah. And also like there's different tiers of it too, because you need a specific amount of initial capital in order to start an aerospace startup. Like, the common baseline I've heard across the aerospace defense community is like 20 million more to create your own startup.
Right, right.
That's because like
That is
aerospace
right.
startups are significantly more complicated than software startup because it involves hard tech and resource allocation and manufacturing. But I would say Earth observation and also like remote sensing that combined with artificial intelligence, which is the hype right now, would be a great way to raise like initial funding with a prototype that doesn't require any like manufacturing or any like hard tech. So yeah, people can like create their idea, make it like affiliated with AI that is solely like a software solution. So I've seen a lot of like orbital mission visualizers or like orbital trackers that leverage AI, like making an AI like, wrapper effectively around a solution that targets the aerospace industry could be a great leeway for people who are interested in starting their own aerospace startup to get their foot in the door in terms of like, initial investment opportunities.
And Kate, are you seeing the monetization of this growth?
Yes.
Are you seeing the ROI, the return on investment, relatively quick? 18 months, you know?
I'm not too familiar with the lay of the land in terms of investment and like, do you mean in terms of like investment or like them making like a credible profit by selling a service that works?
And I do know companies like Maxar, they own the field right now, right?
Yeah,
'Cause
yeah.
everybody goes to them and they're like they own it right now. So,
Yeah.
but maybe that's the interpretation that it's until we get to monetizing it, right, where I can bring liquidity to the market, and then people are going to invest and say, okay, yeah, I will buy, 1,000 shares of your small company because I know it's going to bring profit. Then, but that's the charge that we've been given, and it's a big challenge that we're still trying to work through. So I'm just glad to see someone produce this level of data, and now someone in the field actually being able to maybe give us proof of concept here. So, well, thank you so much.
Thank you for the great question.
Yeah.
Any other questions?
Yeah, I had a quick question about Top of the Foundation. Since it's a data fusion model, it's like 10 data sets?
I'm not yeah, I see 10 around. So
Yeah.
yeah, we have the Sentinel satellite.
Yeah. And so right now it's just annual temporal resolution and 10 meters spatial resolution?
I think so. Yeah,
Do you-
10 meters, you're right. I'm not too sure about the temporal.
I think it's 2007 to 2024 annual.
Okay.
Have you seen any combinations between some of the data sets that are like data fusion models with outside of these 10 or so data sets, and then I know it's very new, like in the last like month or so, but
yeah.
Looking with, like you mentioned, classification for wildfire, for example.
Yeah.
If you have like ground truth from a wildfire, and then looking at like a random forest or something off of the satellite embeddings, have you seen some of these like can be used for forecasting as well, or more classification off and applying other data sets onto it? Because right now it's just the vector embeddings of the data fusion model, like the 11 or so data sets.
Yeah. I haven't seen like organizations like Google implement it, but I've seen like researchers online doing their own independent research, like include other like data collections from other satellite fleets, like commercially available satellite fleets, and then fuse it with something like the satellite V1 embeddings. Yeah, but that's a good question too, and I wonder if they also not only do they use like satellite-based like sensor data, but also like ground-based data. So, for example, like wildfire research, they can use sensor data from like more like land-based systems like UAVs in conjunction with satellite data in order to improve the accuracy of the results.
Yeah, I think that's definitely the difficulty is it's very difficult for researchers. This is very much like a black box for people like DeepMind or Wilbur, people can do it. I know that they have text embeddings in it, but if they can add more and more products into it, like in-situ measurements, but it's just difficult because that's not something you really have to wait for the products.
Mhm.
I think it's definitely the future of the foundational models.
Yeah, there's definitely a lot of implications there across a wide range of industry sectors. So I definitely agree. Thank you for your question.
First of all, I was kind of wondering how you got into this field because obviously you're really knowledgeable of the topic and there's so much to explore in this. And then second of all, I was wondering what new things can be explored with this field? Like what questions can be answered and how can this technology be used to uncover new things that we don't know?
Yeah, those are really good questions. How I got into the field? So I initially wasn't in the aerospace sector. I was initially like a programmer. So I really liked computers and I developed a lot of software solutions. Like the only caveat to that was like I did like flight lessons as a kid. I was like a teenager, I was 16, 17. So that got me into like aviation. And I did a lot of cybersecurity research in regards to planes because you wouldn't think of airplanes as being like highly vulnerable things, but there's a lot of like inherent vulnerabilities amongst like aircraft systems. So I built using like my knowledge of computers and cybersecurity at the time, I built a system to secure the communication of airplanes. So airplanes use a system called automatic dependent surveillance broadcast, which is a radio system operating on 1090 megahertz frequency to transmit information about themselves. So it's similar to AIS within maritime vessels, but it's typically just a simple way for airplanes to know where they are, how fast they're traveling, and where they're located. And it's used by ground-based ATCs, like people who like control airplanes and tell airplanes where to go, to like where they should land, when they should land, and they're widely responsible for the traffic that occurs at airports. But that system could easily be hacked into, and hackers on the ground could do something called spoofing, where they could generate their own airplane and have it show up on the airplane radar. So I created like a little device to detect for that using like an antenna and a software-defined radio. And that got me into like thinking about how software and security can be applied for the aerospace sector. And then from there, I just did a lot of like different projects. I don't know, like I would just like buy like satellite dishes or like have friends give me their satellite dishes and like, rework it to like analyze for different like satellite signals. I don't know, built antennas to make my own satellite ground station. So like little mini projects here and there that taught me more things about the field. I think that's like the best way to learn about anything. It's just like to be hands-on, be interested in it, and pursue a lot of different projects. You seem like you're quite young, so like I would suggest like if you're in school, like joining a club, like a coding club or like a robotics club. I'm sure you're like part of one. Like doing a lot of mini projects that interest you along the way. And to your second question, where do I see the future of this technology going? I think within 5 to 10 years, we're going to see a lot more specialized sensors. So the one, I think I mentioned I can't go back, but I mentioned Sentinel 5C, which has like a really specialized multispectral sensor. We're seeing a progression of satellite sensors where they're getting much, much better. We can think of this as like the progression of the iPhone camera. Like the iPhone 6 camera is significantly worse than the capabilities of the iPhone 10 camera. So, and also like with more, it was a lot harder and a lot more expensive to deploy satellites back in the day. It's a lot easier and more affordable to deploy satellites nowadays. So we're having a lot more satellites with better sensors, better sensor capabilities. So we're going to see a lot more higher fidelity data, which in the short term is going to help improve the data accuracy that is applied to embeddings and artificial intelligence models, like the projects I listed in this presentation. So we'll see much quicker disaster response, like much better like analysis of like crop yields. So I see. So those are the good positive outcomes I see within like the next 5 to 10 years. We also, whatever you're considering a new technology, you also need to like consider how it can be utilized for nefarious purposes. And one of my key areas of concern is we have like another like, there's probably these probably exist, but I'm not wide aware of it. Like another Gorgon Stare project. Gorgon Stare was a project that was deployed by the U.S. Air Force decades ago, and it was a very, very good camera that was put on top of the MQ-9 Reaper drone, and that camera was so good that it could pretty much effectively track where you are, regardless of where you were stationed on Earth, because the camera was so good at seeing things, and that raises a lot of concerns when it comes to voyeurism, like spying, like if we don't give permission for this technology to, I don't know, like, it's a huge, like, privacy issue that could occur, and, like, nefarious, like, institutions or commercial that, like, collect that kind of data in order to sell it is also a cause of concern, and also, like, it's also a geopolitical concern, too, because we're going to be seeing like other foreign nations that try to like analyze land coverage over specifically Air Force locations, Space Force locations, and gather critical intel that we need to keep hidden. And thinking like further down the road, I would say like as we, I would say there's going to be a lot more satellite fleets that conduct like high fidelity scientific research. So like we mentioned earlier, like Mars, exoplanets, potentially. We'll see how far it goes, but I think there's going to be a lot of like scientific research opportunities to conduct with the satellites, which is really interesting and exciting.
I had a comment. I wonder if you have a comment regarding the recent shutdown of some of the polar orbiting satellites, the NOAA 15, 18, 19, and potential shutdown of OCO2 and OCO3, and how the databases for weather monitoring might be affected by all these satellites being eliminated from contributing to the database.
Yeah, the shutdown of those polar orbiting satellites, they kind of, I would say like initially, it could abruptly cause, I don't know, a hassle amongst like researchers that want to get like accurate meteorological data. But there's a wide range of like polar orbiting satellites that are, I don't know. There's also like a NOAA 18 and like a NOAA 19. So I think all those satellites were legacy, right? I'm not too familiar with the NOAA fleet. But I think like in the short term, yeah, we're going to be suffering data losses. There's a lot of like publicly accessible sites that provide like data and like visualization maps to researchers that rely specifically on the NOAA 14 and NOAA 15 infrastructure. And there's also like APIs that like piggyback off of that, and like a lot of applications that people use on a day-to-day basis. So that's going to be a cause of concern. But I think like people will adapt. I think there's going to be like a transition to newer satellite data sets, and also the other like commercial satellites that also publish their own data in like a form of an API or like a data archive.
I have a question that kind of leads off of what Rick was asking about, namely, uh, how do you find a customer base? And how do you monetize things? Why is it worth something to people? And, there's a massive amount of data available. It's not simple to interpret some of this, as some of the math that you were showing was indicating. It takes some resources to evaluate it, and then you want to have what's the payoff for having done that. So, like agricultural purposes, yes. There's a lot of ways in which farmers, agricultural areas, miners can be interested in these things, but we have a real propensity to use things that are free. You need a customer who values it.
Yes.
Sometimes the customer decides they don't value it anymore, like the OCO, and all of a sudden we're going to cancel that out because we don't want it. But how do we get the value established in this data?
Yeah, like it's kind of seen amongst like the aerospace companies I've worked for, although they were not necessarily like Earth observation or software based, is that like in their initial stages they raised most of their capital via government contracts. So this was like applications they found for their system, whether it be like a satellite or the data that is collected by the satellite that they can sell directly for defense purposes.
So the government is prime contractor, prime customer, because
For a lot of aerospace stuff.
we have a lot of interest.
Yeah.
Some of the business cases we've seen is connected to Wall Street. Insurance companies are spying on your roof. And they're saying, okay, hey, you need a new roof, or I'm not going to cover you anymore because your roof looks like it's got some damage. And so, the insurance and the indemnification industry is massive on that, right? So we are seeing some monetization in that perspective, but we just have to identify that government resources and funding trails are finite, right? Are finite. The same thing with the gentleman that asked the question with the polar satellites. NASA is telling us that one of the commercial directors wrote a paper the other day, article, and said, we need commercial industry to take that over because we need to go out further out to the cosmos. We cannot afford to continue circling the globe. So if you do see from the current administration, they're going to cancel a lot of these systems. It's based on, because the premise of NASA is to go on fan out, right? To really push out there. So the next thing you're about to hear is they're going to shut down the International Space Station. And I know I know that's going to hurt a lot of public opinion, but if you want to get to Mars.
Well, do they think they're going to beat SpaceX to Mars? Because I thought NASA's like entire thing.
It's kind of a parallel effort. It's in parallel. But you want commercial providers to beat you to it, of course, right? Because you want competition. But that's what the papers that I'm seeing and from bosses, the directors are. It's probably going to hurt public opinion, just like the space shuttle, right? But those systems are very wieldy, very expensive to run. And I'm not saying they ran their course. We can get out in all the argument about that. But if you want to get to the moon and Mars again, put boots on Mars, it's going to take that. Yeah. And the reality is just because if we don't do it, our adversaries are going to do it, and then you're going to go back to the 1960s again, right? Which is what got us to the moon. It wasn't money. It was the Soviets are going to do it first. So.
Well, I'm already seeing that kind of like aggression.
You're saying we want to be dealing with value rather than
to the low Earth orbit economy, yeah, because I think the number is 40 trillion. There's a $40 trillion monetization to it, but how quick do you make that? How quick do you get there, and what is it to do? So obviously,
who's gonna pay 40 trillion? That's
Yeah, I guess how you create it, I don't know. How do you
that must
generate
be
that?
almost the global economy.
Yeah, oh yeah, how do you generate that? My question to you is one of the challenges that we're having. How do you, this is it's a little bit theoretical because we were just going through some meetings the other day. How do I avoid over-reliance on AI and MMM? And I know there's some, I'm sorry. Yeah. How do I avoid over-reliance, bias on too much AI and LLMs? Because this is what, these are critical challenges that we're facing in the workforce and in our programs. Obviously, generationally, the older workforce is used to doing things the old ways, right? Validating, verifying work. The younger generation wants an over-reliance on artificial intelligence and, the phone and ChatGPT. Some of the business case problems that we've been having, working on one of the launch programs for launch vehicles, we had young engineers that just graduated from school and they were producing the technical memos. And we're like, no. It took our senior workforce that has been through a lot. The data is wrong, guys. This is wrong, that you cannot over-rely on. And I'll give you an example of that. You go to ChatGPT and said, you say, paint me a pictures of astronauts flying into the moon. And it paints little unicorns and cats, right? So how do you address those challenges? What are things that you're seeing in your capacities to make sure we don't go over reliance and make people dumb, right? And I'm sorry, just for lack of a better phrase, we don't want to over rely on it. And at the same time, I get it. You don't want to under rely on it. Maybe there's a middle ground in there. And how do I address that with my workforce, right? When I got young minds that are coming from Johns Hopkins, from USC, right? Hey, it's all about the latest flavor of the day, AI and machine learning. And then I've got Bob that worked on the space shuttle and says, wait a minute, guys. No, you need to validate, verify. Hence, you talked about NASA SLS. Why is it taking so long? Because NASA's culture is to triple down on triple redundancy, right? Or Elon Musk is, let's fly it, blow it up, and do it 10 times over. So I'd like to get your take. How do I bring in my workforce, and how do I find, I'm not going to say a perfect state, but how do I work that, between those two forces? Over to you.
The AI hallucinations and defunks AI is a significant problem. I think traditionally the aerospace industry has been really good at auditing their engineering products because the stakes were so high. So I think just keeping that as a tradition. So SpaceX and Impulse and a lot of other companies, they have something called a preliminary design review. Critical design review. So keeping that up, and I think in this case, generative AI hasn't gone as that far to apply for be applicable for mechanical engineering and electrical engineering. Although there are some software solutions that are viable out there, but I think the major cause of concern right now is software, people writing code and making sure it doesn't. I used to write C++, and I remember when I would write C++ and I would play around with ChatGPT and Gemini, different models to generate the code for me. It would sometimes produce code that would create variables that would induce a segmentation fault or cause the kernel to panic.
Right.
What's going on? What's going on?
Right.
And the programmers couldn't debug it because they didn't understand the underlying principles of the C++ programming. So I think it's going to definitely be an interplay of having the right personnel on board to have a vetting process. So having a senior engineer look over everything routinely, or verify that the AI model is correct. Or we could this could also be another like leeway into the commercial sector would be to like have more um, put more the commercial incentive to have the companies develop specialized artificial intelligence models directly for the aerospace sector. That
Like
would-
validators?
Yeah, validators, yeah. Those would be like the two ideas I have off the top of my head.
And I thought that's where you were going towards the tail end of your presentation, because you took, I think you were taking the three samples or three different platforms.
Yeah,
I think that's, maybe I'm.
yeah, like cross verification, yeah. That's also,
Take a sample of 5, out of 5 platforms, use a minimum of 3.
yeah, like having that redundancy.
Right, yep, because, at our industry days, those are conversations that we need to drive forward. I can't rely on the Nipper GPTs, on just the chat GPTs, right? Maybe I should take a population number and then come up with a formula that maybe a minimum of 3. So it balances or provides a.
Yeah, it's like GPS, like technically you need 3 satellites to find the position on Earth, but they use 4.
Right.
Sometimes.
Yeah. And at the same time, I just don't want humanity to get dumb, right? Like where they're just overly reliant, right?
Yeah.
We had people writing like, weekly technical reports. It's
Yeah.
it's
So
like,
you don't use their brain power?
yeah, I think you have to be mindful of
Yeah.
that.
Yeah, I mean, it could be, yeah, technology has always be like leveraged as a tool. Like I've heard counterexamples to that where like they interviewed, I don't know, Magnus Carlsen the other day, and like he found like a 30-year-old kid that was almost about to like grandmaster in chess, and he attributed that to like the rise of like AI technology and like AI being able to like train people in a way that is like tailored to them, and also like addresses their weaknesses. So like it can also like finding ways to tailor the education system so it leverages AI and doesn't make people dumb. It's going to be one of the fundamental questions about the 21st century. Unfortunately.
Hello, everyone. I am Tatiana. I want to say thank you for the presentation. It's very enlightening and learning a little bit more. I get to camp today through Dr. Kim, who is part of our events that we constantly have. I am part of the Southway Workforce Investment Board. We work in the aspect of workforce development in the Southway area, including 11 cities from Inglewood all the way to the beaches areas, Carson and Gardena. So we collaborate with different entities from small businesses to big companies, big name companies in the area. Sorry, this is part of my name. So some of the questions that has been brought up right now pick on our brains because many of the companies that we work develop between softwares to actual infrastructure, right? And we work with youth and we work with adults. And the youth aspect, one of the biggest questions is like, we have youth that are more familiar with technology and how technology is advancing so quickly. Sometimes it feels like the human capacity is slowing down compared to how fast technology is speeding within the last few years. So some of the youth that we serve may be encountering some of the challenges that slow down the progress through school. And some of the questions that arise is like, how do we create programs that cater for youth and they're capable to enter the workforce that and the demands that we're going to foresee in the future. So for example, your question was like, how do we monetize this, right?
Right.
And then it's like, do we even have the capacity of people to enter that sector to begin with? Because have they learned or have gotten to that capacity? And then the other thing that came to my head out of this is like, for those that are adults and that maybe can be at some point terminated or laid off because the work that they have been doing for so long is no longer to exist in the future. So those are things that in the workforce development we're questioning on how we better serve the population and at the same time how we are moving forward with how the world is moving, right? I myself, I come from a sociology and economics background in academics, so those are questions as well that we have very similar stuff. I think you pointed out how we can use this technology on the work, right? And I think also something else I want to add point aside from what I do for work is I am from El Salvador. Right now, there's a lot of conversations related to the technology of cryptocurrencies and Bitcoin. And so I think that is happening is the studies of volcanoes.
Yeah.
So I am thinking, okay, how this technology can be implemented in the studies of volcanoes. So Salvador has so many volcanoes. It's one of the smallest countries in Central America, but it's also very dense on those terms of the geographical aspect. So I'm thinking, so if we are moving forward to an economy that may rely on cryptocurrencies, but for that aspect, we also need thermal energy. Can this technology be implemented? And can we see that happening in the next 10 to 5 years? Or will technology move so fast that the time will be reduced and the workforce will be only available to that capacity? So if we decide to move out of Earth to other planets or so, I think that can expand the frame, time frame of our workforce. Because an individual, let's say ideally, the time span in the US is like 70 years. And out of those 70 years, if you complete high school, then university, how many years of workforce will we have? 30 years, 40 years is the expectation. So I just wanted to share that aspect of what we do and what are questions that are arising in the workforce. And a little bit of how I was thinking through when other people were mentioning asking.
Yeah.
And one more thing also, I wanted to mention in the South Bay area, we do have a little more of education related to aerospace technology, biotechnology, which in the context of Los Angeles County or at least California is not the same for every school or educational, post-secondary education.
Yeah, that's a really good elaborate question. I guess we can break it down into pieces. In terms of like the rate of acceleration of technology compared to like the rate at which we can provide like educational services, I I don't see that. I think there's still going to be things that are going like even if like we get to a point where we can teach the machine to do most of like the labor for us, there's going to be still things to discover. Like, we hardly understand the nature of the universe itself. There's always things to learn. Um, there's a wide range of like optimization problems across a wide range of domains like physics and technology. It just finding a way to integrate artificial intelligence systems into the youth as young as possible, and making that like an imperative part of the education system. Um,
But I think we return to the question that he had, like how do we verify the information we're obtaining through artificial intelligence is veridic or certain, right? So I think that breach is like we are jumping into the what I am obtaining from this is actually what is the ultimate truth per se.
yeah, like who's to say like what my LLM model outputs is actually true, like based on ground truth. Yeah. I guess like that also adds to the point like there's always like things to learn about the nature of the universe itself. Like we have like most science that was like invented hundreds of years ago had its own like shortcomings and like were disproven. I think it's just going to increase the rate at which like we learn and like, discover things about the universe. So I think there's always going at least like within I don't think it's there's still going to be like an incentive to have like an education system where people like proper personnel like are trained to learn. And I think like there's going to be more like courses and curriculum that center around like artificial intelligence and how that could be integrated into like into the workflow of like how we think of industry and like how we think of research and how we think of engineering. Yeah, but it's hard to see like 200 years, 500 years down the road. I think AI safety needs to be emphasized, so we don't like end up in a PDUM situation, in the Matrix where like the machines take over and they use the humans as batteries to generate their own energy. It might not end up to be like that intense, but there are like very scary, like large language models can output very scary things if you prompt engineer it the right way to give you things it shouldn't be giving you. So increasing more initiative on how we have more governance and AI policy, so we can ensure that the well-being of our species is going to be pivotal. And like having more education regarding like technology. I would say that would be my short-sighted question, but you can check with the question. Any more questions? Do you have any questions online?
Nothing from the audience?
Nothing online.
Yeah, I have a question online. I was just wondering on your thoughts.
AJ, can you say?
You mentioned there.
AJ, can you say who you are? What's your name?
Yeah, I'm sorry. My name's Adrian. Question. I just have a question regarding what the presenters' thoughts might be on. I guess what you might relegate as the citizen science category. And I know you mentioned there a little bit earlier that you'd had some experience with SDR radios and reworked satellite dishes, perhaps to pick up some satellite communications. And there's a significant worldwide group of individuals that routinely, as private individuals, download, for example, imagery from weather satellites, the Meteor and GOES satellites, for example. Yeah. And these individuals do post a lot of their images. For example, in the Reddit amateur satellite subreddit, there's a number of individuals that routinely publish these satellite images. So I'm just curious what your thoughts are regarding. There's been all this conversation regarding the commercial aspects of satellite databases for ground-based observations, for example. So I'm just curious what you might think about the potential contributions of just individuals in perhaps maybe more widespread. Some of these databases are now being more privately held and inaccessible. And so I was just curious what you might consider in terms of private individual type contributions of for submission of some of these images and so forth for ongoing public accessible databases.
I really like that question. There's a really surprisingly large community of people online that most of them are amateur radio operators. So they have some kind of like ham radio background that are able to access and tune into these satellites. And tuning into a satellite isn't that expensive. All you need is some kind of if you want to listen to the International Space Station, for example, all you need is a directional Yagi antenna that's tuned to the frequency of the International Space Station. You're able to tune into it. Same line of reasoning goes for weather satellites, which are ATP based. Other commercial satellites. You can also tune into commercial satellites too, depending on their packet, what packet format they use, and their demodulation, whether you have access to demodulate their signals, and if they make if they're unencrypted and they make their modulation screens public. So obtaining that information would be accessible to to like hobbyists or people who have some kind of background with antenna systems. I thought about this, and I think crowdsourcing specifically for satellite signals intelligence is going to be very relevant for defense applications. So for example, there's this app online that detects for GPS jamming, and GPS jamming was very significant during the Ukraine conflict because you didn't want like aircraft to be flying over um, like Russia or Ukraine. So what those forces did was they would have jammers on the ground that would jam GPS. So UAVs that would fly overhead of those areas would get the incorrect positioning information, and that could cause collisions and like effectively disorient themselves within the environment. And um, that was crowdsourced in a way, like so that system used ADSB, and it used and ADSB can pretty much be collected by anyone because it's an open-ended frequency. So people that are ground-based could submit their data to that data set in order to detect for GPS jamming. So there's a lot of military systems that leverage signals intelligence, and provided with the right background knowledge and equipment, anyone could contribute to like a crowdsourced project in order to help with defensive initiatives, but also with like research initiatives as well. If there's a specific satellite that's publicly giving down data, which can be crowdsourced, that's also another viable option. And we're also seeing like a big boom. It's a localized like boom, but within like cheap commercial radio technology. So a lot of you might have heard of Meshtastic. That's like a radio system used by a lot of like hobbyist radio operators, and that's a LoRa system, long range radio system, that allows for like people to communicate with each other without the internet, so within a remote environment. And LoRa works great, especially if you're far away from the person who's receiving your signal. So, and this hashtag has been extremely popular amongst the electronics and radio community. So I do see a lot of interesting. So yes, I do see a lot of implications of like crowdsourcing data and having like, real world people, not just organizations, be able to access and tune into whether it be like satellite signals or UAV signals in order to provide information for research initiatives and commercial initiatives.
Yeah, for you mentioned the ADSD data. That's easily downloadable and obtainable with current sort of aircraft maps that are all available for individual observations. And so and I'm glad you mentioned the mesh static networks that are popping up everywhere that enable the sort of communications outside of the internet type of networks. But yeah, so I was just curious what your thoughts were on perhaps the utility of some of these databases that might be used publicly without any commercialization, sort of either uh, uh, subjected to censorship or other types of manipulation by commercial entities and that kind of effect.
Yeah, to your point, there when it comes to like crowdsourced data, there's going to have to be like a rigorous vetting process, because like who's to say the data you obtained from a random individual is actually correct and isn't from like a foreign adversary that's trying to like put a bunch of garbage in your data to trick you. Um, and I think by the nature of it being crowdsourced, you have enough data redundancy to like pinpoint outliers, and by pinpointing outliers, you can do like a trace route of who submitted the data and be able to actually identify any people that are trying to like mess with your network or mess with your data source. So it's kind of like decentralized like crypto technologies in a sense, like because it's like such a big network, there's a lot of like redundancy and protections in place in order to make it effectively secure. So I would say that would be my response to that.
Well, thank you for your response.
All right, well, I want to be respectful for everyone's time, so we're gonna have to call it there. Let's give Angelina another round of applause. Thank you for your talk and answering all of our questions. We really appreciate it.
It was a lot, it was a lot.
Right, so many different subjects. It's
Right,
amazing.
right. Thank you. Have a good night, everyone.
I like your scale shirt. You have scale?
My hearing is almost gone. All right. Oh, yeah.
We'll have to invite you to an industry day over.
Or
something. Yeah, especially as a younger.
We're not in
Takes
upstate.
a lot of the caring.
He's there.
You have a lot of interns.
Yeah.
They do it very easy. I like to use.
Yes.
A lot of people that.
Very good.
Let's take how you get that. Where's some activity? Yeah. I'll send you the thing of this, plan that.
Probably source. Just right for us.
Okay, for the,
Get that
graphics.
That's
not military.
How's life at Cal State?
It is.
Right. We don't have those. It's good. Second year, third.
So it's just as hard.
Oh, yeah. That shows. It always comes
I
back.
think of maybe
Definitely, hit you with a lot there.
I was gonna tell you as well.
You work on projects.
Yeah, I mean,
You're good lodging,
we have a similarity.
Well, okay.
yeah.
I'm gonna put in, I put my name on previous, for 2 months.
Yeah, yeah. Oh, nice, okay.
So that's part of it. And,
Right,
the solar system will get removed and replaced.
I just came back from Johns Hopkins. So I'll do,
Get
get a chance to replace.
Wait, do you know Sydney's name?